In our study of infinite series, we're starting to look at a variety of different tests that will tell us whether or not a given infinite series diverges or converges without us needing to find the limit of partial sums, which in most cases isn't possible to do anyway. We've already talked about the divergence or nth term test, which says that in order for an infinite series to converge, the very least that must happen is that the terms themselves must approach zero. But even if that happens, that doesn't guarantee convergence. So we need some other tests to make this determination between divergence and convergence. So I'm going to develop an argument here for something called the integral test. And here are some of the things that I'm going to do in terms of developing my argument. First of all, I'm assuming that I'm starting with an infinite series of positive terms decreasing to zero, one which has a chance of converging. And what I'm going to do is I'm going to represent the terms of my series as areas of rectangles. Here's what I mean. If I have a rectangle, I'm going to use the height of my rectangle to represent the value of a given term. So for example, term 1, its height might be a1. The width of the rectangle will always be 1. And if I do it this way, you'll see that the area of the rectangle also represents the value of term 1. So we're representing our term values through areas. And then I can continue to do term 2, represent it as an area, term 3, represent it as an area, and then if I find the sum of all areas, what I'm doing is representing my infinite series geometrically. The other thing I'm going to do in terms of developing an understanding of the integral test is I'm going to introduce a function f of x, which is a positive continuous decreasing function. And it's going to be created so that the value of the function at k will match the value of the kth term of the series. Alright, here's a visual representation of what I'm talking about. So I have my rectangles, term 1, term 2, term 3 represented as areas of rectangles. And I've got a function f of x which is continuous so that the left endpoint of each rectangle is equivalent to the value of the term. So this is the value of term 1, a1. It's also f of 1. This is the value here of term 2. That's f of 2, etc. So I've got a function such that the value of the kth term is equal to f of k. And now I'm going to make my argument. I'm going to talk about the area under the red curve as well as the area of all the rectangles. And through what you see, it will make sense that all of the areas of rectangles will be greater than the area under the red curve from 1 to infinity. So we can agree with this argument, which I can then write like so. This is the infinite series. And so we're saying that the infinite series value is greater than the definite integral value. And the conclusion we can draw from this is that if our definite integral diverged, it being smaller than our infinite series, that would mean that the infinite series would also have to diverge. So there's one half of the argument of the integral test. Now what I'm going to do is I'm going to represent my areas using a right endpoint. So I still have my function, f of x, but this time it's the right end of each interval that matches the kth value of the series. So a1 is f of 1, a2 is f of 2, a3 is f of 3, etc. And from this picture, we will see that area 2 plus area 3 plus area 4, etc. is below the value of the definite integral from 1 to infinity, which represents the area under the red curve from 1 to infinity. So this statement makes sense visually from our picture. That statement can be written as so. And I think it makes sense then that if our definite integral converged, anything smaller than it must converge, so the series converges. But you might say, well, my infinite series though is starting with k equals 2. Don't we want it to start with k equals 1? Alright, well we could do that by adding on a1 to both sides. But adding on a fixed value to both sides of the inequation won't change the convergence or divergence of either side. each side will still converge as it did before, and so our argument is suggesting that if the definite integral converges, then the infinite series will also converge. And this is the second part of what we call the integral test, which, if you put both of those results together, looks like this. If we let the terms of our series equal the function value at x equals k, and we have f of x being a positive, decreasing, and continuous function, then we're saying that if the definite integral converges, the series converges. And if the definite integral diverges, the infinite series diverges. So what we're saying is that the infinite series behaves the same way as the definite integral. We can determine the convergence of a series by looking at the corresponding definite integral. Now, in most cases, you'll keep the index below here the same, although it doesn't really matter because, as we said in another video, deleting a finite number of terms doesn't change the convergence or divergence of a series. If you want to see the fine print on the integral test more generally, we're saying that the integral test is valid for any infinite series, no matter where you start, provided that for some value greater than 0, your function is positive, decreasing, and continuous on that interval. You can then determine the convergence of the series by evaluating this integral. Finally, I need to emphasize that if you find that your definite integral converges to a value, the value that this converges to is not the sum of the infinite series. The fact that it converges to a value is just saying that this infinite series converges to some value that you would have to estimate with a calculator or calculate in some other way. So let's use the integral test to show that this series diverges. Now, you should recognize this infinite series as the harmonic series, which we've already shown in a previous video diverges, but we want to show it in this case using the integral test. So we have our formula here that generates the terms of the series, and we want to create a function that matches that at k, so that would be 1 over x. And the integral test says we're going to evaluate the integral from 1 to infinity of 1 over x dx. This is an improper integral, so I need to represent it properly with the limit. So that's ln absolute x as x goes from 1 to p, limit and as p goes to infinity, ln p goes to infinity, minus 1 is 0, so this is infinity, so it diverges. So to justify our answer, since f is 1 over x is positive, continuous, and decreasing, and the integral of 1 over x dx diverges, therefore the corresponding series diverges. When you're justifying your answer, be sure you mention all of the conditions of the test, the name of the test, and the thing that you've shown that justifies the test. Okay, follow-up question. For what values of p will this infinite series converge or diverge? Alright, now you'll notice that this is pretty much the same question as the last, 1 over k, except that we have a power of p on the k. And this is an important kind of series called a p series. So 1 over k to the p. We've already shown that if p equals 1, the series diverges. That's what we showed in the last example. Okay. Now, depending if p is more than 1 or less than 1, we're going to see that this important series diverges or converges. So we're going to use the integral test to find out when it converges and when it diverges, when p is not 1. So we start off with our definite integral. We're going to represent our function as 1 over x to the p. So we need to represent this as an improper integral. And my antiderivative will be x to the increase the power by 1. That'd be 1 minus p divided by the new power as x goes from 1 to m. And this will reduce to 1, so let me just rewrite it one more time. Alright, time to evaluate our limit. What this evaluates to is going to depend on our value of p. So let's consider p greater than 1. If p is greater than 1, our exponent is going to be negative. And that's going to mean that this is going to approach 0, since it's going to go to the denominator, and m is going to infinity. In other words, all of this is going to wipe out, and therefore our integral that we started with is going to evaluate to negative 1 over 1 minus p, or 1 over p minus 1. In other words, it converges. It's approaching a finite value. If p is less than 1, then our exponent here will be greater than 0, and that will mean that our term m to the 1 over p is going to go to infinity as m goes to infinity. In other words, our definite integral diverges. Putting all this together, if we have a p-series, sometimes called a hyperharmonic series as well, this series will diverge if p is less than 1, but let's not forget p equals 1, which we showed earlier. So it will diverge if p is less than or equal to 1, and it will converge if p is greater than 1. So when you see a p-series, you can apply this directly since we've already proven it. The other thing I'll just mention is don't mix p-series up with geometric series. Here's just one more perspective on p-series. This is an animation from the Wolfram Demonstrations Project website. I have my improper integral of 1 to infinity of 1 over x to the 1, p is 1, shown here, and you can see that the area is infinite, which of course it should be since p is 1. If p is more than 1, you'll notice that suddenly the integral becomes defined, calculatable. It's converging, in other words. If we go smaller than 1, though, then it's infinite. It diverges. So p equals 1 is that magic place on the function 1 over x to the p between when the integral diverges and converges, and therefore the corresponding series converges or diverges.